So we're going to just ask the question, when momentum is changed, so we're talking about a car and a collision or something like that, what force is involved? And the formula for working it out is that force is equal to change in momentum divided by change in time. Okay, so the little triangle, the delta, just means change in. So we need to consider how much the momentum has changed and how long it takes to change that momentum. Okay, and that will, if you make the change in time bigger, dividing by a bigger number means a lower force. Okay, so the longer the time takes, the less force is involved, which is why, as I was saying before, cars are built to crumple and things like that, so the actual slowing down process takes longer. Okay, so let's look at, for an example, we'll look at this one we had here, the car crashing with the truck, and we'll look at the change in momentum of the car. So ask the question, what goes on? So let's say that this whole collision with the car hitting the truck, from the time it starts to the time it's actually wrecked and moving back the other way, say will take half a second. Okay, so this collision in half of a second. Okay, and we want to ask, what's the force exerted on the car? Okay, so using this formula, it's change in momentum. So looking at the car here, how much did the car's momentum change by? So we need to know the momentum of the car after the collision. So it's momentum before the collision, we've got. What's the momentum of the car after the collision? Nick's reaching for his calculator. He's going for it. We'll do commentary on this, commentary on Nick with the calculator. He's looking at the board, he's getting the figures. Yeah, he's got them in, he's laughing now, he's lost concentration. It's not helping that Fritz is laughing at him. But yep, there we go, he's got it. Got one number in. He's asked a question now. Yeah, we've got a delay. Okay, so we're trying to find the momentum of the car. So just the car bit. So looking at, it's kind of misshapen now, but the car is going, so the mass of the car is still the 1200 kgs. And the velocity of the car is now the 7.33. So to get the momentum, you're just going to go that 1200 times the 7.33, and that'll give us the momentum of the car after the collision. Nick's been given some advice now. 8,796. Okay, so that's the momentum of the car after the collision. So the momentum of the car before the collision was 18,000. Momentum of the car after the collision, 8,796. So how much is the momentum of the car changed by? 9,204 is one option. Scott's nodding, you happy with that? So where's that coming from? That number minus that one? Yeah. Anybody want to raise some concerns about this? Ricky thinks he wants to because I've asked the question. It's obvious I want concerns, but he doesn't know what they are. Okay, so before the collision, the momentum was in that direction. After the collision, it's in that direction. So how much does the momentum change by? You have to add them. It was going that way, and now it's come back and going this way. So the amount that it's changed, it's lost all of that and gained that. So the total change in momentum is that number plus that number. Yeah? Or you could think of this as being negative because it's going the opposite direction. So that minus that, with that as a negative number, will give you the right answer. So the change in momentum is 18,000 minus negative 8,796 mathematically, or you can just think of it that way and that way, so you have to add them together. So that gives 2,6,796. And the change of time we decided was half a second. So you work that out, that's going to be 29535. That sound all right? Well, let's have a think, how big is that force? So this is the average force acting over that half second. So what's the units for that going to be? Newtons, because it's a force. Yeah. So somewhere around about 53 kilonewtons. 54, if we do it to one around it sensibly. So we're talking about 54 kilonewtons, 54,000 newtons. So that's the equivalent of, divide that by 10, you get 5,000, so about 5 tons of mass. So the force exerted gravitationally by 5 tons would be the force required to make that car turn around and start going the other way. And that's the average force that should be exerted. So the person sitting in the car for half a second is being squashed by a 5-ton mass, effectively. The equivalent of having 5-ton mass sitting on top of you for half a second. Probably makes a bit of a mess. I've rubbed the brick out now, so it's a bit hard to try it. Okay. But that's a legit way of calculating the force that's involved in a collision with change in mass. Okay. And the force on the truck will be exactly the same, because the change in momentum for the truck has got to be exactly the same the other way, because the total change is nothing. If the car's changed by this much, the truck must have changed by the other amount. So going back, the truck will have the same momentum change the other direction, will have the same force the other direction, which makes sense with Newton's third law. You know, every reaction has an equal opposite reaction. So whatever force the truck's putting on the car's putting the same force back on the truck the other way. And that all comes out in the math when you do this. It works out fine.